So, our Gibbs energy reactor, Mr. Gibbsy, just going to call this gas, and let's come over here, specify a pressure drop 2 bar, and bottoms, let's just call this liquid, and voila. So, let's see what we have here. Do take note of our flow rate 250, and we have a flow rate of 339. So basically we gained about 120, 130, and nothing at the bottom. Everything is in the gas stream. And take note of the temperature, 943.5. Now that's more like it. A proper exothermic reaction. But remember, we're having two reactions: the partial oxidation, which generates the heat needed to drive the SMR. So basically, the heat was generated from the exothermic reaction of the partial oxidation, and then some of the heat was used for the SMR, and this is what we are left with. But let's take a look at our product yield. 44.45. What's our target again? Our target is less than 15 methane slip, unreacted methane basically, greater than 150 kilomole per hour, and hydrogen concentration of 50 mole per hour. So we head back and we basically did not meet the target. Mission unsuccessful, unfortunately. But then let's try and outsource and see if we could tweak some things a little bit to try and meet the target. We're currently at 60 Celsius. Take note, so the temperature here is 44.5. Remember that we were supposed to be at the temperature of 85, between 25 Celsius and 85 Celsius. That was supposed to be the temperature. So we've already determined that with the 25 Celsius oxygen, we cannot meet the target. So let's say our oxygen was at a temperature of 85 Celsius. What would that look like? Would we be able to meet the target? That's 608, and our temperature out 946 Celsius. Nah, we still can't meet the target. So unfortunately, we can't meet the target with that specified conditions. But let's say, for example, we were to have, we're just outsourcing. Basically, at this point, we were able to generate hydrogen, as we could tell. Let's check the flow rate of our hydrogen before we conclude anything. We have a total flow rate of 379.5 and a hydrogen concentration of 44.6%. So we're going to multiply the molar fraction by the molar flow rate to get the total flow of hydrogen. So 0.4460 times, what was that again? 379.5. We have a total flow of 169.25. 169.25. That's quite ironic. 100 and basically approximately, let's just say approximately 170 kilomole per hour. So in terms of the hydrogen flow, we passed, but the hydrogen concentration for our, hydrogen concentration in our syngas stream is less than the target. So the question is a bit flawed, but we will take responsibility. We don't win every day, do we? So basically, we could say mission partially successful. Now, the magic we've been waiting for. Heat recycling, not to waste heat. We're going to inject this hot stream back into these two heat exchangers. Let's see if it's something that would work out successfully without temperature crossing. Remember the temperature crossing phenomena? If you're not aware of, if you're not aware with that, what that is, you should check that out. And we're going to call this out, shell out one, unknown P. So we're going to need to specify our pressure drop also. We're going to give it a 0.5 bar also. Well, why not? And voila! It works without a temperature drop, a pressure drop rather. Not a pressure drop, temperature cross. It works without temperature cross. So let's see what the new temperature looks like. 686.9 from 900 we dropped in terms of temperature, and the reason for that is basically change in temperature difference, and we have more flow rate over here plus our latent heat energy. All that works to our advantage, but we will most likely have a temperature cross here. So let's see. Hmm. Let's give this 0.5, and let's go and specify our. Did we inject that? No, we did not. Shell out one. Let's call this shell out two. Basically a temperature cross. It didn't work, unfortunately. FT correction factor low. It's just basically trying to tell us a temperature cross. It doesn't work, unfortunately. I was really looking forward to seeing that, it's very magical, always. It's always magical. So I'll just straighten this out. No, it's not too straight, but so what we're going to do is that we are going to lower the bar a little bit. I mean, we can't waste all that heat, can we? We're going to lower the bar. We're going to lower the bar because it's futile. We were not able to accomplish the mission, so why not just make the recycling work out? Well, the target we set for our outlets here was 685, but then it doesn't work. So let's lower that. Let's say that the temperature was, raised from 382 to about 450. Let's see if that works in our favor. It does. Would you look at that? Let's be a little bit curious. 500. It does work. 550 does work. 600. It does work. 650. Temperature cross. Let's walk backwards. 630. Doesn't work. 620. Doesn't work. 610. Does work without a temperature cross. Let's squeeze out as much energy as we can. 615. Does work. 618. Maybe not. 619. Doesn't work. So let's just stay at 618. That's a very good place to be. And we're still left with a temperature of 606 Celsius. That's how hot and how much latent energy that stream carries. So you can see the reason why engineers do love this process so much. The ATR process, so much energy for use. You can see that, and then our stream over here comes out as at what 586.4. Basically, it doesn't really affect us that much. So let's see. 44.16. It dropped from 44.45. We're still, I'm pretty much sure we still passed the benchmark for the flow. It's just the concentration of the hydrogen. And also our carbon monoxide is supposed to be the most second most component present. But the funny thing, the catchy thing here is that there is still one more reaction, one more step we would take that would take us where we need to be. But this content has been stretched out too much. We're all exhausted. So that would be our potential next content. water gas shift reaction. Now, this is a reaction that uses, after an SMR, we're certainly left with unreacted water. In our case, you could see 29% unreacted water, and carbon monoxide 23%. So water gas shift reaction does is that it combines carbon monoxide and water together to produce product of carbon dioxide and more hydrogen gas. That's where we have more hydrogen gas in our process. It goes to our advantage. Basically, instead of leaving unreacted water, we're still breaking down the water to produce hydrogen gas, and then this carbon dioxide takes an oxygen molecule, oxygen atom, and then it becomes carbon monoxide. But we're going to definitely leave that for our next content. As you can see, our methane slip is certainly less than 15%. It's just 2.93%. So, not to be too hard on ourselves, this is a mission partially accomplished. If you followed us down this far, as always, please make sure to like, subscribe, and click on the notification icon. And we will see you in our next content. Ciao.